っくりレ夢ムです。
ゆっくりマリサだぜ。
Hi, Raimu Marissa. Hey guys. Maxwell's demon, the tiny monster that almost broke the laws of physics.
ゆっくりしていってね。
Section 1. Hook imagine a tiny creature. So small it could sit on a single molecule. This creature has one job. It stands at a door between two rooms full of gas. It watches the molecules flying around on both sides. And whenever a fast molecule comes from the left, it opens the door. Whenever a slow molecule comes from the right, it opens the door. That's all it does. Open and close a door. But here's the thing. After a while, all the fast molecules are on the right side. All the slow molecules are on the left. One side is hot, the other is cold. The creature just created a temperature difference from nothing, without using any energy, without doing any real work. And if you can create a temperature difference from nothing, you can run an engine forever. Free energy, infinite power, a machine that never runs out. A perfect violation of one of the most ironclad laws in all of physics. This is Maxwell's demon. It was invented in 1867, and for nearly 100 years, nobody could prove it was wrong. Section 2. The story begins to understand why Maxwell's demon is so dangerous. You need to understand what it was attacking. The year is 1867. The place is Edinburgh, Scotland. James Clerk Maxwell is already one of the most celebrated scientists in the world. He unified electricity and magnetism into a single theory. He predicted the existence of radio waves decades before anyone detected them. His equations still appear on t-shirts worn by physics students today. But in 1867, Maxwell isn't thinking about electromagnetism. He's thinking about heat. And he spotted what looks like a crack in the foundation of physics. The target is the second law of thermodynamics. The second law says, in simple terms, that heat always flows from hot to cold, never the other way. Disorder always increases. You can't unscramble an egg. You can't make a shattered glass reassemble itself. The universe moves in one direction only, toward greater disorder. This law seemed absolute, unbreakable. Every experiment ever run confirmed it. Every engine, every furnace, every steam boiler, all of them obeyed it perfectly. Maxwell thought he had found a loophole, not a real one. He didn't think the second law was actually wrong. He was a careful scientist. He was posing a thought experiment, a Gedanken experiment, as the Germans say, to probe the foundations of the law and find out exactly why it was true. He described his tiny creature in a letter to a friend, calling it a finite being. Section 3. The evidence. Let's build the case piece by piece. Because the mystery of Maxwell's demon isn't just about a door in a box. It connects to some of the deepest questions in physics, and the evidence that eventually solved it came from a completely unexpected direction. First piece of evidence. The second law is statistical, not absolute. Here's something Maxwell understood that many of his contemporaries didn't. The second law of thermodynamics, heat flows from hot to cold, disorder always increases, is not a fundamental physical law like gravity. It's a statistical law, a law of probability. In a gas, molecules are flying around in all directions at all speeds, some fast, some slow. Temperature is just the average kinetic energy of those molecules. Heat flows from hot to cold because there are vastly more ways for energy to spread out than to concentrate. But vastly more ways is not the same as impossible to do otherwise. If you waited long enough, an incredibly, inconceivably, absurdly long time, you might see the molecules in a room randomly arrange themselves so that all the fast ones ended up on one side and all the slow ones on the other. It wouldn't violate any fundamental law. It would just be extraordinarily improbable. Maxwell's point was subtle. The second law holds because of probability, not because of some deeper physical prohibition. And if that's true, if it's a matter of probability rather than absolute prohibition, then maybe a clever enough entity could beat the odds. Not by waiting for a miracle, by actively sorting. That's the demon. Second piece of evidence. Why sorting seems to cost nothing. Here's what makes the demon so genuinely threatening. Opening and closing a frictionless door takes essentially no energy. If the door is perfectly hinged, perfectly frictionless, the demon can open and close it millions of times without expending any significant work. Observing a molecule, just looking at it, also seems to cost nothing. Light bouncing off a molecule to tell you its speed doesn't have to add energy to the system. Or does it? In 1867, Maxwell's contemporaries had no framework for answering that question. The physics of measurement, the physics of what happens when you observe something, wasn't developed. And without that framework, the demon seemed genuinely undefeatable. The molecules sort themselves. The temperature difference appears. You run an engine off the temperature difference. The engine produces work. The work could be used to, say, keep the demon fed and operating. And the whole system runs forever, producing energy from nothing. A perpetual motion machine, built from information. But that's where things became strange. Third piece of evidence, Szilard's shocking discovery in 1929. 62 years after Maxwell invented the demon, a Hungarian-American physicist named Leo Szilard took the problem seriously in a way that changed everything. Szilard stripped the demon down to its simplest possible version. Not a complex sorting creature, just a single molecule in a box. And a demon that knows which half of the box the molecule is in. If you know where the molecule is, you can extract work from it. You insert a partition, let the molecule push against it, and harvest the energy of that push. Szilard calculated exactly how much work you could extract. A specific, measurable amount tied to the fact that you have one bit of information about the molecule's location. And here's his crucial insight. That work, the energy you extracted, is exactly equal to the energy it costs to acquire one bit of information. Not approximately equal. Exactly. The demon isn't getting something for nothing. It's converting information into energy. And information, it turns out, isn't free. Szilard had found the hidden cost. The energy to measure the molecule. The energy to acquire the information about where it was. At first, this seemed to solve the mystery completely. Then investigators looked more carefully and discovered something unexpected. Fourth piece of evidence. Measurement alone doesn't cost enough. For decades after Szilard, physicists assumed the cost was in the measurement. Looking at the molecule required interacting with it, bouncing a photon off it, or something similar, and that interaction necessarily added energy to the system. This seemed to close the case. The demon pays for the temperature difference by spending energy during measurement. But in 1961, a physicist named Rolf Landauer at IBM ran the calculation more carefully, and he found that measurement, in principle, doesn't have to cost energy. You can measure something reversibly, without irreversibly adding heat to the system. So measurement wasn't the answer. The hidden truth was somewhere else, and it was hiding in the most unexpected place, the demon's memory. Section 4. Theories. The case is more complicated than it appeared. Multiple investigators have proposed solutions. Let's go through the serious ones. Theory 1. The cost is in measurement. Szilard's original answer. Szilard's 1929 paper proposed that every act of measurement, every time the demon observes a molecule, requires the expenditure of energy equal to the information gained. The logic: to learn something about a physical system, you have to interact with it physically. And physical interactions cost energy. Therefore, the demon is paying for its information and energy. The second law is preserved because the energy cost of measurement exactly offsets the energy gained from sorting. The strength: it was the first rigorous attempt to close the loophole. It connected information and thermodynamics in a way that was genuinely new. The weakness: Landauer proved in 1961 that measurement can theoretically be done reversibly, without irreversible energy cost. If measurement can be free, Szilard's answer doesn't fully close the case. The demon could measure without paying, and the paradox revives. Theory 2. The cost is in erasing memory, Landauer's principle. Rolf Landauer's 1961 paper is considered one of the most important contributions to the physics of information in the 20th century. Landauer's insight: the demon has to remember each measurement it makes. Is this molecule fast or slow? Left side or right side? It stores that information somewhere in its memory. When you delete a bit of information, you release a specific, calculable amount of heat into the environment. Not approximately. Exactly. There is a precise minimum energy cost to erasing one bit of information. It's called Landauer's limit. And Landauer showed that the heat released by erasing the demon's memories is exactly equal to the work gained from sorting. The demon doesn't get free energy. It pays for its sorting with the cost of memory erasure. The second law is preserved, not through measurement, through forgetting. The strength. This is now the accepted solution. It was confirmed experimentally in 2012 by physicists in France, who built a physical version of Landauer's erasure and measured the heat release directly. The weakness. It's deeply counterintuitive. The cost isn't in doing work. It's in erasing information. That's a genuinely strange place for the law of physics to hide its enforcement mechanism. Theory 3. Charles Bennett's interpretation. The demon can delay but not escape. In 1982, physicist Charles Bennett at IBM extended Landauer's work and provided the clearest version of the complete solution. Bennett showed that the demon can, in principle, run for a while without paying any energy cost. It can measure for free. It can sort for free. It can even store the information for free. But eventually, it runs out of memory. And when it has to erase that memory, when it has to reset its internal state to continue operating, that's when the bill comes due. Every bit of information erased releases heat. And the total heat released across an entire cycle of operation exactly balances the work extracted from sorting. The demon cannot escape. It can delay payment. But the accounting always catches up. The strength. It's the most complete version of the solution. It explains why the demon seems to work for a while, because erasure hasn't happened yet, and why it ultimately fails. The weakness. It requires accepting that information is physical, that erasing a memory has thermodynamic consequences, that the abstract concept of forgetting has a real, measurable energy cost. This is philosophically radical, even if it's now experimentally confirmed. Theory 4. Maybe the demon works, and the second law is only approximate. This is the minority position, but it exists and serious physicists have held it. The argument, the second law is statistical. Maxwell was right about that from the start. Statistically, sorting should be paid for. But in a sufficiently clever implementation, a sufficiently small system, a sufficiently fast demon, maybe the statistical fluctuations allow brief violations. On very small scales, random fluctuations can temporarily decrease entropy. Experiments have confirmed this. Tiny particles in solution can briefly move in statistically improbable ways, gaining energy from their environment for a moment. If those fluctuations can be harvested, if a real, physical demon could capture them before they average out, maybe free energy could be extracted at the nanoscale, even if the second law holds on large scales. The strength, it's not entirely wrong. Statistical fluctuations are real. Entropy can decrease briefly in tiny systems. The weakness, these fluctuations are self-limiting. Harnessing them requires a mechanism that costs at least as much to operate as the fluctuations provide. Every serious analysis of physical demons finds the same result. The second law holds. The accounting always balances. Section 5. The most likely answer. Here's what the full investigation reveals. Maxwell's demon is defeated. But it took 90 years, 2 revolutions in physics, and a deep reconceptualization of what information actually is. The solution is Landauer's principle, confirmed by Bennett's analysis and experimentally verified in 2012. The demon's fatal weakness is its memory. Every act of observation produces information. Information takes up physical space, in neurons, in transistors, in any physical system that can be in different states. That information has to be stored somewhere. And when the storage fills up and needs to be reset, when the demon has to forget what it learned, that erasure releases heat. Precisely the right amount of heat. Exactly enough to cancel the work extracted from sorting. The second law doesn't fail. It doesn't even bend. It just turned out to be enforced in a completely unexpected place. Not in the sorting, not in the measuring, but in the forgetting. This has a deeper implication that physicists are still working through. Information is physical. That's the hidden truth the demon reveals. Not just approximately physical. Not just practically connected to physics. Fundamentally, irreducibly physical. A bit of information, a yes or no, a 0 or 1, a fast molecule or a slow one, has thermodynamic consequences. Erasing it costs energy. Creating it from nothing is impossible. Information obeys conservation laws. This is the birth of what's now called the physics of information, a field that connects thermodynamics, quantum mechanics, and computer science in ways that nobody anticipated before Maxwell's demon forced the question. The demon's legacy is bigger than its defeat. It asked, is information physical? And the answer, arrived at through 150 years of some of the best minds in physics, is yes, the demon lost. But physics was never the same after the fight. Section 6. Conclusion. Here's what I keep thinking about after working through this entire case. Maxwell invented the demon as a thought experiment. A letter to a friend. Not a paper, not a formal publication, just an idea he was playing with, trying to understand the foundations of a law he was pretty sure was true. He didn't think he had found a real loophole. He thought he had found a puzzle that would force physicists to think more carefully about why the second law actually worked. He was right about that, just not about the timeline. The puzzle took 90 years to fully resolve, and along the way, it forced physicists to develop statistical mechanics, the framework for understanding how macroscopic laws emerge from microscopic randomness. Information theory, the mathematics of information developed by Claude Shannon in 1948, which gave physicists the tools to even discuss the cost of measurement and erasure rigorously. The physics of computation, the recognition that computing, like sorting, has thermodynamic consequences, and that any physical computer must pay a minimum energy cost to erase information. All of that, from a demon that was never supposed to be real. The 2012 experiment in France is worth pausing on. Physicists built a physical system with a colloidal particle, a tiny bead suspended in liquid, and used a computer-controlled laser to track the particle and selectively push it uphill in an energy landscape. They extracted work from random thermal fluctuations, using information to do it. And they confirmed that when they erased the information stored in the computer controlling the laser, the heat released matched Landauer's prediction within experimental error. Landauer's principle isn't just theoretical. It's measured. It's real. Here's what stays with me about this case. Your phone's processor erases information billions of times per second. Every computation, every app, every scroll, every message involves erasure. And every erasure releases heat. That heat is Landauer's limit, multiplied billions of times. It's real energy from real information erasure. It's the reason your phone gets warm in your hand. Maxwell's demon lives inside every computer ever built. And every computer defeats it the same way, by paying the thermodynamic cost of forgetting what it no longer needs. The most ironclad law in physics wasn't defeated by a demon. It was defended by the price of a memory. And the next time you feel your phone get warm, that heat is the universe collecting what it's owed. Every deletion, every cleared cache, every forgotten bit. The second law always gets paid.